Okay, welcome back to a new physics video. As you might know, the Commission of the European Union has decided some time ago to only allow emission-free cars on the street after the year 2035. Therefore, I would like to discuss today the pros and cons of such a decision from the physics point of view. So as a first step, I want to take a look at the efficiencies of converting different forms of energy into mechanical motion. The easiest way, of course, to convert heat energy into motion is to use a steam machine, which you might know from school. However, this device has a very low efficiency of around maybe 5%. The problem here is that first you have to burn the fuel material, then you have to create steam, and then you have to convert the steam into mechanical motion with the help of a turbine, for example. And this process is unfortunately highly inefficient. So in the case of a diesel or petrol engine, you can avoid some of these steps by directly burning the fuel and then converting the heat energy or the chemical energy of the fuel into the mechanical motion of the engine cylinders. And this leads to a much higher efficiency of approximately 20 to 35%. However, and this one has to keep in mind that this is already very close to the maximum efficiency that can theoretically be achieved with this method of burning fuel because of the laws of thermodynamics, which can of course not be broken. And one can easily understand the reason for that by imagining the particles in the hot gas as small spheres that move in all directions of the three-dimensional space due to their thermal energy. This is a fully stochastical process, of course, and it already makes clear why only a small fraction of that energy, of the kinetic energy of the molecules, can be converted into the linear motion of a car actually. So one example to understand that problem a little bit deeper is by taking a look at a stone lying on the ground. So if all molecules in that stone moved upwards at the same time, the stone would actually make a small jump. Nevertheless, our intuition already tells us that the probability for such a process is very small. It's actually negligible and it can be assumed as impossible. This is the reason why heat energy is usually referred to as an inferior type of energy, whereas other forms of energy such as mechanical energy or electrical energy are superior types. Because you can always convert mechanical energy into heat with an efficiency of 100%, but you can never convert heat into mechanical energy with an efficiency of even close to 100%. It's always in the range of, under normal conditions, in the range of maybe 20, 30, maximum 40%. And when we now take a look at electrical engines, we can immediately see that here this problem does not occur, because the electrons inside the wire already move in a certain direction, and therefore the transformation from electrical energy into mechanical energy, into linear motion of a car is much higher, usually even higher than 90%. And in fact, it only depends on losses due to resistivity in the battery or in the cables, for example, or in some other frictions, which you also have, of course, for classical cars. Nevertheless, the overall efficiency from the charging station to the tires is approximately 60 to 70% in total, which is of course not 100%, but already a very huge improvement compared to efficiency of classical cars that burn fossil fuels. Electric cars have one more advantage compared to fuel burning cars, in addition to the much higher efficiency, and this is related to the conservation of energy. So if a car accelerates, its kinetic energy increases, and in an ideal world, the kinetic energy of the car remains constant after reaching the final speed of, let's suppose, 50 km per hour. And if you then decelerate the car because of a red traffic light or because of an accident, for instance, then an electric car uses the possibility to convert this kinetic energy back into fuel, into electricity, and this method is called recuperation. And this works because you can always use the electrical engine also as a generator, and the other way around, of course. In the case of fossil fuel, this is of course not possible because it would just not be possible to convert the kinetic energy of the car back into new petrol or diesel. So such a car which burns fossil fuels can only use conventional brakes, which converts the kinetic energy of the car into heat and making it impossible to take back the work which has been used for the acceleration process. So a conventional car therefore requires energy to accelerate, which is then lost, whereas an electric car can convert that energy back into electricity. And this is another huge advantage of electrical mobility, since it increases the already very high efficiency of an electric car even further. However, in the real world, of course, you have additional energy losses during the driving, such as large variety of frictions, air resistance, and so on. So the energy which is used to work against these forces is then simply lost. And this is true, of course, for both engine types. There's no difference between electric cars and fossil fuel burning cars. And this can easily be understood by imagining that you drive with a car at a certain speed and then you remove your foot from the gas pedal. As you will see, the car will then get slower in time until it comes to a complete stop eventually. So for a simple calculation, we want to assume that the most important friction of a car is the rolling friction. And I think a typical value for that is around 0.01. This value has to be then multiplied with the mass of the car. So let's suppose 1000 kg and the G factor, which can be assumed of, or which can be approximated as 10 meter per second squared. The resulting friction force is then given as 100 Newton. And in order to obtain the required work from that, we have to multiply this force with the travel distance of, let's suppose, 100 kilometer. So computing this total product then leads to a value of 10 million joule, respectively watt seconds. And we can now convert this value into kilowatt hours and dividing it by the caloric value of petrol, which is close to 8.5 kilowatt hours per liter, and taking then also the efficiency of petrol cars into account, the final result is by a factor of around 3 larger, which leads to a theoretical fuel consumption of 1 liter per 100 kilometer. And from this very simple example, or from this very simple calculation, we can immediately see that the petrol consumption scales nearly linear with the weight of the car, which means that every additional ton increases the petrol consumption by around 1 liter, depending on the actual value of the friction constant. Another important friction is, of course, the air resistance, which scales with the square of the speed. And the reason for that is that the car transfers some of its kinetic energy to the air molecules that then gain speed from that. In order to calculate the numerical value of the resulting force, we can use the well-known formula given as given as the force equal to 1/2 times the density of the air times the cross section of the car times the drag coefficient, which is usually denoted as CW or CD. And this can vary in between 0.9 for very old cars like the Model T from Ford, which has been produced in the beginning of the last century, and values which are even better than 0.1 for highly optimized cars. For most of the cars which can be bought nowadays, I think a value of around 0.3 is a good assumption according to my experience. And then inserting all these values into the given formula shows that for speed levels around 120 km per hour, the value of the air resistance already gets higher than the one of the rolling friction. So in order to save fuel and to increase the traveling distance, which you can travel, the maximum achievable speed of an electric car is usually limited by the producing companies to values around 130 km per hour. However, of course, this might change in the future when the batteries when batteries with larger energy densities will be available. Nevertheless, the conversion of energy gets more and more inefficient for higher speeds. Therefore, a limitation in that is maybe also a point which has to be discussed in the future. These frictions about which I talked before are of course not the only ones which have to be taken into account. In general, one can say that modern petrol cars consume around 6 liters per 100 kilometer. So you have additional frictions. Here, just one example, assuming the petrol consumption for a randomly chosen car for a certain traveling distance is 51 kilowatt hour. In the case of an electric car, the energy consumption would be then by a factor of 3 smaller, around 15 to 20 kilowatt hour, because you have factor of 3 higher efficiency. Official studies have shown that in Germany around 7 billion liters of petrol and diesel are consumed for transportation every year. And taking then the previously mentioned caloric value for petrol into account, this equals energy consumption of around 200 to 300 terawatt hour. And the resulting value was divided by a factor of 3 again because of the assumed 30% efficiency. And currently Germany produces 600 terawatt hour electrical energy per year. And this means the production of electricity has to be increased by around 50% in order to produce enough energy for all electrical cars and to substitute petrol cars, which seems to be possible. But of course, and we have to be honest in this case, it is challenging to do this with renewable energy. And of course, the usage of renewable energy is the key point here, because if the energy comes from burning fossil fuels, such as coal or gas, for example, then of course the effect on the climate change is absolutely zero, because you just only replace one fossil fuel with another one. However, even in that case, there is still the great advantage that the pollution is not directly emitted by the car, but outside in the suburbs of the city, for example. So this is still a possibility to keep the cities cleaner and increase the life quality significantly. In Germany, there's already a high amount of energy which comes from renewable sources. My local electricity provider, for example, promises that it delivers 100% renewable energy to the houses in our city. And another important factor is, of course, the distance that can be traveled with a fully charged battery compared to a filled fuel tank. And if you travel with a car that has a petrol consumption of 6 liters per 100 kilometer and a fuel tank capacity of 60 liters, then you will be able to travel 600 kilometers without any interruption. The newest car batteries have typically values around 50 to 60 kilowatt hour storage. And assuming a consumption of 15 kilowatt hours per 100 kilometer, as we have said before, you can actually travel up to 400 kilometer. However, in reality, it is only maybe around 300 kilometer because of the efficiency, battery degradation, climatic influences, since of course every battery also has an optimum working temperature, which is usually in between 20 and 40 degree, and as soon as the outside temperature moves away from that optimum, the efficiency decreases. And this effect can be especially seen in the winter time, when the temperature can drop significantly below the freezing point of water, so below 0 degree. And in summertime, if the temperature climbs to values above 50 degree, of course it will not damage the battery, but it also decreases the capacity. So an additional installed air conditioner, which you need for this high temperature and also for the cooling of the battery, might also increase the fuel consumption significantly. Nevertheless, the short traveling distances should not be an issue, because many car drivers state that they actually like to make breaks during their driving after traveling a long distance. So if the car battery can now be charged with a power of, let's suppose, 100 kilowatt, which is possible nowadays with superchargers, for example, then the battery will be fully charged again after a short time of around 30 minutes, which would be enough to maybe visit the restroom or to drink a cup of coffee. Although there are battery breakthroughs expected in the near future, the status quo, I think, seems to be already sufficient, or at least promising, if enough charge capacity can be provided. And of course, when we talk about the physics of electric mobility, we have to talk also about the chemical process in the battery. So this is a key parameter of an electric car, and also which can be seen as a negative point of electromobility because of the huge amount of lithium which is used in order to produce batteries for electric cars. Around, I would say, 30% of the lithium which is produced in Chile. And previous studies have shown that a huge amount of water is used for that process, which can then also make huge areas in Chile becoming a desert. However, a quite modern study has proven the opposite. For 64 kilowatt hour battery, for example, only around 4 tons of water have to be evaporated. And this is equal to the usage of the production of around 250 gram beef. And this is quite less. Additionally, there is a huge development in the sector of battery recycling, which makes it possible to reuse the material from old batteries and also decrease the requirement of new lithium. And if there is a battery breakthrough in the near future and lithium could be replaced by natrium, for example, many of the problems would become obsolete because the availability of natrium on the Earth is almost unlimited, and most important factor, these batteries do not require materials like cobalt, nickel, copper, like the batteries nowadays, and this also should make the battery cheaper than, for example, lithium-ion batteries. And the predicted energy density of these so-called sodium-ion batteries is around 150 watt-hours per kilogram, and therefore you can say equal to the one of the actual lithium-ion batteries which are used. So an electric car that uses these types of batteries will not be heavier than the one using a lithium-ion battery, and even the overall costs could be reduced by using sodium-ion batteries, which can also solve in addition many problems. Therefore, I would say that when new battery types are available, even now already, but even if new battery types are available, the reason for using electric cars increases even further. Another important issue which is commonly discussed in media is the complexity of an electric car. So this can be an advantage or disadvantage, of course. And the problem is that the engine of electric car is much simpler than the one of a petrol car. And this requires in general much a smaller amount of parts, which decreases then also the number of companies that have to produce the related components and spare parts. So therefore, in general, one can say that less people are required, which can lead to a higher unemployment rate, especially in countries that mainly produce these car components. On the other hand, there is, of course, in the future more manpower required in the development of new technologies, such as batteries, new software, artificial intelligence, and so on, which might then compensate this loss of possible working positions if one can just simply substitute one position with another one. So I think all the important points are discussed, and coming to the conclusion now, when taking all these points into account, I would say electromobility has indeed a very high potential to become the best climate-saving technology in the near future, if not the only one. However, there are still questions unanswered, and the effects on the society especially should be investigated further, not only from the physics point of view, of course. And the next question is then, of course, if individual transportation is still the future or not. Maybe it will be better in the future to completely shift away from cars and go to a public transport system. But this cannot be discussed in this video, of course. Then of course, and thank you very much for watching this video. I hope that you liked it, that you learned something new. If you like it, please hit the like button, please subscribe my channel if you have not done so far, and if you don't want to miss any further videos, then hopefully I will be able to make some new content very soon.